Okay, what we did in 5.1 was approximate areas underneath a curve using rectangles. Okay, and then in this section we're actually going to get to the exact areas underneath the curve, and they are called definite intervals. And the author also talks about Riemann sums. And I will tell you, our calc book figures it a little bit differently than most calc books. Most calc books will figure the area underneath a curve using rectangles, rectangle approximation. Then it would do trapezoids, okay, and then it would do the exact area. Your book does rectangles, exact area, then the trapezoids. So the order is a little bit different than most calc books, but it'll still work. Okay, I'm going to give you a curve, and I want you to run the RAM program that we did on the calculators. Okay. In y sub 1, I want you to put in negative 1/3 x squared plus 5x plus 7. Okay, now I'm going to give you a specific window. Okay, for x, the x min I want it to be negative 5. The x max I want it to be 20. Okay, and the scale I want it to be 5. For the y min, negative 10. The y max is 40. And the scale I want it to be 10. Okay, now I want you to run the RAM program that we linked yesterday, and it should give you all three answers. And if you have a long list of programs, you can get down there quicker. You can either scroll down to the R RAM program, or you can do alpha R. Okay, the A for this one, we're going to do the first vertical line would be where A is 0, or where X is 0. The B, the second vertical line, is where B equals 15. And we're going to do five slices or subintervals. They switch what they call them, slices or subintervals. Okay, so run the program. Our A is 0. So we're going to figure the area, the approximation from 0 to 15 and 5 slices. Okay, and you think, you can't hardly get to 1001, 1002, and it's got all three answers. That has to make you appreciate what all is going on inside that calculator in just a little bit of time. Okay, so you end up with the RRAM is 285. Okay, the mid-RAM, and actually, hang on, the MRAM was 296.25, and the left. And remember, the RAM stands for Rectangular Approximation Method. We're figuring the approximate area underneath the curve using rectangles. Okay? Everybody agree with that? Did you get it to work? Okay. Now, I want you to watch on my calculator. I'm going to run a different program. Okay? Same equation, same window, same A, B, and subintervals. Different program. I'm going to run the program on mine called area. Okay, the A is 0, the B is 15, and 5 subintervals. Not only does this one figure the answers, it draws the picture. Okay? So, that would be real easy then to draw. You know, it's a parabola that opens down. Okay? And from 0, we're going to end up with so many slices. And this one, it's doing left-hand endpoints. So it's doing something like this, like this. I didn't get them quite all in there, something like that. Okay. Now you notice the worm cursor up here? It's frozen. Okay. So it's giving you time. Whoever programmed this said, okay, let's give them time to draw that on their paper. Now press enter. There's the 285. Okay, press enter. It redraws the picture. Now which one's it giving me? Left-hand endpoints or right-hand? Right-hand endpoints. So you'd have time to draw the picture. Then there's your answer. Okay, and then it will go again. Draws it. Now it's doing the mid. And it would give you time to draw your picture. And there's your answer. So the RAM program is good, but somebody said I can make it better. Okay. Now remember, if you wanted to see what this program is, everybody look up here for a minute. Okay, I'm just going into program. I went right over to edit. You know, they had to ask you to input the A, the B, and then this is what all it takes to do that program. So somebody had to go through some work, okay, to get it to work. Okay, it didn't just happen. Okay, would you like to have that program? Okay, okay. So let's link. Okay, so that area program will draw the pictures and figure the rectangular approximation for you. Okay. Okay. Now, what they're going to do is they're going to take and you can actually go online and look for a rectangular approximation method calculus for figuring areas. But what they're really doing is they're going to take each slice and they're going to make the slice thinner. Okay, and that's why yesterday when you did the homework, you went from 10 rectangles to 100 to 1,000, and you should see the approximations are getting closer and closer to the exact area underneath the curve. Okay, and the exact area underneath the curve is actually what they call the definite integral. So first, they're going to write it as a limit. The limit, and I'm not that concerned about the, this formula. You're not really going to use this, but I want it in your notes. Okay, if you take the limit, and it's basically the areas of the rectangles, and the areas of the rectangles, they're using instead of using f of x, okay, they're using the f of c sub k times the delta x sub k, and the delta x is the change in the width, or the width of each rectangle. Okay, and k is going to go from 1 to n, and it's as the norms go to 0. Now, there's a lot of information that goes with that formula, and I'm going to let you look at that in the book. The one that we need is if you let the width go to 0, okay, then you get what they call the definite integral. Looks like an elongated S. That's the integral symbol for f of x with respect to x from A to B. And the A and the B are just like our vertical lines. Okay, and we will go through some more of this, but this is the main formula, okay, for a definite integral. And the definite integral is the exact area underneath the curve from A to B. Okay. The author goes through a theorem that says all continuous functions You realize how long that's been since we talked about continuity? That was one of the first things we talked about, all continuous functions. Basically, it means if you can draw the graph without lifting your pencil, okay, it's continuous. All continuous functions are integrable. Okay, that means you can integrate them. That means you should be able to find the area under the curve. That also means the definite integral exists. Okay, and then the author says if y equals f of x is non-negative and integrable. That's kind of hard to say. Try saying that. Integrable over closed interval and the closed interval is our two vertical, okay, like from A to B. Then the area under the curve from A to B is, and it's basically what we just set up above. It's A equals, the area equals the definite integral of our function f of x. Now, when you read this with respect to x. Okay, that just the definite integral of f of x with respect to x. If I was using a polynomial with a t in there, then it'd say with respect to t. It would have a dt at the end. Okay, and it's from A to B. So that's the main formula for area underneath a curve. Okay. Now, on your calculator, we spent a lot of time doing the numerical derivative, right? Math 8. Okay. Look under the math key. We spent a lot of time on that, the numerical derivative. I'll go down one more. The function integral, math 9. Okay. If you went to look this up in the calculator manual, the function integral, okay, so it's the function integral, like that. It's the function integral, and what it would say is the function integral, you put that in first, okay, then you put in your variable, then you put in your lower limit, then you put in your upper limit, and all of these are separated by commas. And then the tolerance, we're actually going to use the default. Okay, and then you press enter. So, for what we did up above, okay, take a look at this. If you go back up above, this was the right, and that was an approximation. That's a mid, that's approximation, and that's an approximation. They're all close to like 285 to 296. Now, this is going to figure the exact area underneath that curve from 0 to 15. So, when we put it in the home screen, we're going to do, now, I already have it in y sub 1, so I can use that, or I could type in the whole equation again. Okay, I'm not going to type in the whole equation. Yeah. Different. It's going to look a little bit different, you know, and we'll figure that out. So on this one, we're going to do math 9, and since I already have it in there, I'm going to do bars y sub. I want to put in y sub 1. Okay. and the variable I'm using an x. I went from 0 to 15, so my lower limit is my a, my upper limit is my 15. Okay, and the tolerance, like I said, we're not going to mess with that. Okay, close the parentheses. So if you want to, for right now, we're not doing that. We're just accepting the default on the tolerance. Okay, so we want okay, and then you press enter. Okay, and that is the exact area underneath the curve. Okay, this is the exact area under the curve.